Let's take a look at this example here. So in this example, we have a plate that is made from two different components. Component A is very smooth and component B is rough. So the surface temperature is given to be 35 for both cases, for both surfaces. The surface temperature is 35. And air is flowing above these surfaces at 10 degrees Celsius and velocity is 25 meters per second. So our goal is to find what is the total convection heat transfer across these surfaces. So we have two possibilities in case 1. A is coming first, B is later. In case 2, B is first, and then we have A second. So first I want you to pause here and think, do you think there should be a difference when we change the order? If so, why? Okay, I want you to think about this a little bit. All right. So now let's solve this. All right. So let's start to write down what we know about this. Start to write down the knowns here. So we know the surface dimensions and characteristics, surface characteristics. One is rough, the other is smooth. And we know the temperatures. Okay. And our goal is to find compare the heat transfer rates, in particular convective heat transfer rates. And schematic is here, so let's also write down the assumptions. So we'll assume properties are constant. Okay, so now we need to look up the properties, and as I mentioned before, properties. So when you are dealing with when you need to calculate Reynolds number and Prandtl number, you need to know what temperature you need to evaluate, because some of the properties are extremely sensitive to temperature. And we learn about a concept called film temperature. This is Ts plus T infinity over 2. Okay, so we need to evaluate the properties at T film, which is 35 is the surface temperature, T infinity is 10 divided by 2, which is 22.5 degrees Celsius, which is roughly equal to 296 Kelvin. Okay, so now I need to look up the properties, or I need to interpolate at this particular point. The kinematic viscosity at 296 Kelvin is 15.5 10 to the minus 6 meters square per second. K is the thermal conductivity. This is 26 times 10 to the minus 3 watt meter per Kelvin. And the Prandtl number is 0.708. Okay, so these are the properties. So now we are ready to move on to the analysis. So the analysis, basically the main thing that we want to compare. So we have two configuration. A is smooth, B is rough. We have A first, we have B first, A. So what is the difference between these two? So that's the question I ask you. So in this case, in case 1, so since you have a smooth plate, so you'll start with a laminar flow, and then as soon as the airflow reaches the rough section, you'll reach the turbulent flow. On the other hand, when you have a rough start, the roughness will induce turbulence immediately. So the airflow will be tripped by the roughness, and then you are going to have roughness and turbulence will not go back to laminar. It's going to continue. So in one case, you start with laminar and transition into turbulent. In the other case, you start with the turbulent immediately. So now we are going to see the effect of this in heat transfer. So first thing I need to do is calculate the Reynolds number. Reynolds number is simply U infinity LC divided by kinematic viscosity. LC is here this length, okay? So we want to know first if there is a transition before we reach plate B. So we don't actually know if this length is enough to reach, enough to keep it all laminar, or if there is a transition. So we want to just make sure we want to know what is the length that is required to have transition. So this is 5 times 10 to the 5, which is the criteria for transition. And we know the velocity, 25 meter per second, that's the incoming stream velocity. Kinematic viscosity is 15.5, 10 to the minus 6. And LC, which is the length required to reach transition. LC is 0.31 meter. So now, and we knew that LA and LB is equal to 0.5. L total is 1 meter. So that means this picture should be changed. So that means the transition happens at 0.3 and then continues with the turbulent. Okay, so it doesn't go laminar up to plate B. Okay, so that is the main message from here. Now we have a situation. So we start with laminar. We start with laminar flow. Let me redraw this. So we start with laminar flow and then transition into turbulent. And this is A, this is B. So this is a mixed flow regime. So we need to get an average property. So the average Nusselt number for this case, we talk about this equation. So we have 0.037 times Reynolds number to the 4/5 power minus A multiplied by Prandtl number to the 1/3 power. So this equation is valid when the Prandtl number is between 0 and 66, and the Reynolds number is between critical and 10 to the 8. So now we need to calculate a new Reynolds number because we are calculating a whole, we are calculating a Reynolds number for whole system, which is U infinity L total divided by kinematic viscosity. In this case, so the velocity is given 25, L total is 1 meter, divided by 15.5, 10 to the minus 6. Everything is metric unit. We have 1.6, 10 to the plus 6. So now, and I substitute everything. A, we mentioned this in the slides. This is 871. So the Nusselt number will be equal to 0.037, 1.6, 10 to the 6 to the 4/5 power minus 871 multiplied by 0.708 to the 1/3 power. So if you do the math, you'll get 2270. And we are almost there. And the Nusselt number is equal to H L divided by L. So multiplied by L divided by K fluid. And this is equal to 2270. And what I'm trying to calculate is the Nusselt number. And that is basically 2270 multiplied by Kf divided by L. So if you plug in everything here, Kf was, we just saw it here, we wrote it down here. So 26 times 10 to the minus 3. And this is 1 meter. So we have 59.1 watt meter square per Kelvin. This is the average convective heat transfer coefficient for case A. It's a case 1. Okay. So now we need to repeat the same thing for case 2. So we need to repeat the same thing for the case 2. In this case, we don't have laminar region. Everything will be turbulent. So we don't have the minus formula. We'll be using average Nusselt number over the fully turbulent flow. And the equation is 0.037 1 times 6 10 to the 6 to the 4/5 power, multiplied by 0.708 to the 1/3. So basically we don't need to subtract 871 section. So that is the difference between laminar and turbulent flow. So in this case we will calculate the Nusselt number, and this is 3050. So that means HL, H times L over K fluid is 3050. So that means HL for case 2 is 3050 multiplied by Kf fluid divided by L. In this case, we will be getting a number. In this case, we will be getting 79.3 watt meter square per Kelvin. So, and we are asked to find, we want to compare. So obviously, case 2 will give us a higher average convective transfer coefficient, because in general, turbulent flow introduce a better heat transfer. We talk about this in chapter 6, because the fluid not only flows in X direction, but also in Y direction. So in general, turbulent flow leads to a higher transfer rate. So that's why we can claim that case 2 has higher heat transfer rate. And if we need to calculate heat transfer rate, so let's just do that for case 1. So for case 1, the heat transfer rate is HL average multiplied by area surface multiplied by Ts minus T infinity. So in here 59.1 watt meter square per Kelvin. Area is, so we need to go back to this diagram here. So we have 0.5 by 1. So the area is 0.5 multiplied by 1. This is meter square. And delta T is 35 minus 10. So we get 737 watt. So basically, in this chapter, so what we'll be doing, we'll be calculating H average, and then we'll be using our previous information from chapter 1 through 5 to calculate the heat transfer rate, effectiveness. So all of the concepts that we learned, let's say lump capacitance method, node equations, resistances, so on and so forth. So we can still use these concepts. So only thing that we need to know now, we don't know H bar, we need to calculate it, and then we will move on to the analysis as we did in previous chapters.